Okay, in this video, we're going to do some more problems involving Kirchhoff's current law. Now the question says, find I0 and I1. So let's look at our circuit now, right? And this looks like a circuit we have never seen before. Now it might be a little intimidating, but let's just start with what we know. So we want to find I0 and I1. We know I0 is going to be the current in this branch, and I1 is going to be the current in this branch. So we know we're going to use KCL to find these currents. Therefore, the first thing I'm going to do is I'm just going to label all of the essential nodes. So I know this is going to be a node, and it's going to be an essential node. I'm going to label that 1. I know this is also an essential node. I'm going to label it 2. This is an essential node. I'm going to label it 3. I know this up here is an essential node. I'm going to label it 4. And finally, our last essential node is going to be right here. I'm going to label it 5. So we have 5 essential nodes in this particular circuit. Now they want us to find I0 and I1. So let's try to find I0, right? Now when we try to find I0, there are a few ways we can go about this, right? We can take the KCL at node 1, and if we was to do that, we can say KCL at node 1. That's going to give us, we know the current entering is going to be equal to the current leaving. The current entering this node is just going to be I sub 0. So we can write I0 is entering the node, and the current that's leaving the node is going to be I1 plus 5 milliamps. So we're going to write this as I1 plus 5 times 10 to the minus 3. Now when we look at this, we have an equation for I0 and I sub 1, but the problem is we cannot find I sub 0 or I sub 1 because we have two unknowns. Therefore, we're going to have to do a different approach, right? So we know the relationship I sub 1 has with I sub 0. To find I sub 0, all we have to do is say I1 plus 5 milliamps. So for right now, we're just going to put this equation to the side and we're going to look at a different node. Now, we still want to find the current that is I sub 0. Now, we know the two nodes that we're going to be looking at is node 1 and node 5. Because I sub 0 is going to go into node 1, but it's leaving node 5. So when we look at KCL for node 5 now, we're going to start with the current that's entering the node. The current that's entering node 5, we can assume is going to come from this branch here. So even though in this particular circuit, they do not have a current to represent this branch, we're just going to have to draw in this current. So I'm just going to draw in this current here, and I'm going to label it I sub 8, right? So we know I sub 8 is the current. We assume the direction of it. We don't know for sure, but we're going to assume that this current is going to enter into node 5. So we're going to assume the direction of the current is going to go this way. Now we could be wrong, and we'll know if we're wrong if we get a negative current. If we get a positive current, then we know we're correct. So we're going to write this as the current entering, which is I8, equals the current leaving, and the current leaving this node is going to be I sub 0, which is going this way, plus 3 milliamps, which is going this way. So we can write I sub 0 plus 3 times 10 to the minus 3, close brackets. So now we have another equation. Now when we look at this, we still cannot technically do anything with this because we don't know what I sub A is, right? But when we look at this particular situation, we have to get comfortable with trying to analyze what's really happening, right? So if we assumed that the direction of the current IA is going to be in this direction here, coming downwards from node 3. If we was to take the KCL of node 3 now, I'm going to do it right here. We can say the KCL at node 3. So we can write this as 2 times 10 to the minus 3 plus 4 times 10 to the minus 3. That's the total current entering this node. Now the total current leaving node 3 is just going to be the current IA. So we know that's going to equal IA. So when we solve for this now, we can say the total current IA is going to equal to 6 milliamps. So 6 milliamps equals IA. Now this is very important, right? This isn't our answer, but this can help us in solving one of our answers. Why? Because we have a relationship for I sub 0 and IA. Now we know IA is 6 milliamp. So what we're going to do now is we're going to plug in this value into the KCL equation we found for node 5. So we know IA equals 6 milliamps. So we can now rewrite this as 6 times 10 to the minus 3 equals I sub 0 plus 3 times 10 to the minus 3, close brackets. Now we want to find I0. This is very easy to find. All we're going to do now is move this over to the next side, but I'm going to rearrange the equation. So I'm going to say I sub 0 equals, now when we move this over to the next side, we're going to get 3 times 10 to the minus 3 amps, which you can also say is going to be 3 milliamps, or 0.003 amps. So this is going to be our answer for I0. Okay, now that we have I0, when we look back at our first equation that we wrote, which was the KCL for node 1, we also had an equation, and this equation formed the relationship between I0 and I1. Now because we just found out what I0 is, all we're going to do is plug in this value into this equation and solve for I1. Therefore we can write this as, we know I sub 0 is 3 milliamps. I'm just going to write it as 3 times 10 to the minus 3 equals I sub 1 plus 5 times 10 to the minus 3. If you want to, you can just take this over and leave it just the way it is. So for this example, that's what I'm going to do. So I'm going to say 3 times 10 to the minus 3 minus 5 times 10 to the minus 3 equals I sub 1. Now when you solve for this, you're going to get the answer negative 2 times 10 to the minus 3 equals I1. Therefore you can say I1 equals negative 2 milliamps, or 0.002 amps, and that's going to be negative 0.002 amps. So this is going to be our answer for this particular problem. So we have successfully solved this problem, and we found the current I0 and I1. Now by the way, because we have a negative current here, we know the direction they gave us for I1 in the original drawing is actually not going this way. It's really going to go this way, towards node 1. So because we have a negative current, all we have to do now is just flip that direction and we'll have a positive current. Okay, let's do another example. So we're going to do this example here, it says find Ix, Iy, and Iz in the circuit. So we know we're going to be using KCL to find the missing currents. Now the first thing I'm going to do is just label the essential nodes. I'm going to call this node 1, node 2, 3, node 4, node 5. Okay, now that we've labeled all our essential nodes, the first thing I'm going to do is try to find a KCL equation for Ix. Now we know the current Ix is going to be in this branch here. So the current Ix is going to deal with node 4 and node 3. So you can choose any one to begin with. There are no direct instructions on which node you should start from. I'm just going to choose one. So for this particular example, I'm just going to choose node 4, right? So I'm going to do KCL at node 4. So remember, the total current entering a node is going to equal the total current leaving a node. So the total current that's entering this node, which is node 4, we know it's going to be 12 milliamps. So we're going to write 12 times 10 to the minus 3 equals the total current leaving. We're going to have 3 milliamps. So I'm just going to write this as 3 times 10 to the minus 3 plus the current I sub x. Now when we look at this, we can say, well, we can find I sub x because we only have one unknown. Therefore, we can take this over to the next side. That's going to give us 12 times 10 to the minus 3 minus 3 times 10 to the minus 3 equals I sub x. Therefore, Ix equals 9 times 10 to the minus 3 amps, which we know we can write as Ix equals 9 milliamps. So this is going to be our answer for I sub x. And we were able to find it just using KCL at node 4. Now mind you, if you use KCL at node 3, you would not have gotten this answer right away. So there are multiple ways you can solve these problems. Sometimes it's trial and error. For me, I just chose node 4 randomly, right? Not even realizing that I actually knew two currents already that's either entering or leaving node 4. Therefore, to find the third current, it was very easy for me to do because this essential node only had 3 branches. If I chose node 3, I would have had to draw in a current for this particular branch here, which means I would have had 2 unknown currents and 1 known current. So this one would have been a little more work right away to find the current Ix. Now that I know the current Ix, I'm going to set my sights on to the current Iy. Now where's Iy? Well, we know Iy is right here in this circuit, right? Now the two nodes we can look at is either node 1 or node 2. It's really up to you. The one I'm going to decide to look at is going to be node 1, right? You can choose node 2 if you like. I'm just going to choose node 1. So we know we're performing KCL. I'm going to say KCL at node 1. So when I look at this now, I know at node 1, the current entering this node is going to be 0. It seems that there is no current entering this node, which seems kind of odd, right? It seems very odd that no current is going to be entering this node. So I'm just going to have 0 equals the current leaving this node. I'm going to have negative 12 milliamps. I'm going to write this as negative 12 times 10 to the minus 3. I'm also going to have I sub y leaving this node, so plus Iy And we're also going to have the current in this branch, which is IZ. So we're going to have plus IZ. Now I'm just going to rearrange this equation to look a little better. So I'm going to write this as I sub y plus I sub z equals 12 times 10 to the minus 3. Now because we have two unknowns, there is nothing we can do. So what we'll do for now is we're going to have to leave this equation, and we're going to have to take the KCL of another essential node, and maybe if we find something that can help us, maybe we can come back to this. Who knows? So we're just going to put a little dent in this for right now, and maybe we'll come back to it, right? Now let's look at another essential node. So we did node 4, we did node 1. Alright, we want to find I sub y, so let's look at node 2. Now when we look at node 2, for example, we know the current that's coming in from this branch. We know the current coming in from this branch. We know the current coming in from this branch. And all of these currents seem to be entering this node. So because I see that, I'm just going to make an assumption that we have another current that's going to go in this branch, but this current is actually going to go away from node 2. So I'm going to assume that this current is going to go in this branch. And I'm going to label this current I sub A. So now that I've labeled this current I sub A, I'm going to use Kirchhoff's current law at node 2. So I'm going to come down here, and I'm going to say KCL at node 2. The total current entering this node is going to be 3 milliamps plus 2 milliamps plus I sub y. So we're going to have a total of 3 times 10 to the minus 3 plus 2 times 10 to the minus 3 plus I sub y equals, and the total current leaving is a current we just put in there, and we drew it to go away from node 2. We called it IA. So we're just going to say this equals IA. Therefore, we can simplify this to be 5 times 10 to the minus 3 plus I sub y equals IA. Now when we look at this, this once again does not help us. Why? Because we have two unknowns. We have IY and we have IA. When we look at our node equation for node 1, we have IY and IZ. We cannot do a system of equations. And the reason is, even though we have the same IY, we do not have IZ in our second equation. So we're going to have to go back and look at our circuit to see if now we can find an equation for IA. So we look at IA now and we say, wait, what are the two nodes that IA is connected to? Well, we know IA deals with node 2 and node 3. So we just did Kirchhoff's current law for node 2. Let's do Kirchhoff's current law for node 3 now. So I'm going to write this as Kirchhoff's current law. I'm going to do it right here. Kirchhoff's KCL at node 3. We know the current entering this node is going to be I sub x, so the current IX, and IA. So I'm going to write IX plus IA equals, the total current leaving is going to be 4 milliamps. So I'm just going to write this as 4 times 10 to the minus 3. Now we have two unknowns once again. But remember, we just found IX, and we know IX is going to be 9 milliamps. So we're going to plug this into our equation for node 3. And we're going to now write this as 9 times 10 to the minus 3 plus IA equals 4 times 10 to the minus 3. Now let's solve for IA. We can say IA equals, we're going to have 4 times 10 to the minus 3 minus 9 times 10 to the minus 3. When you solve for this, IA is going to equal to negative 5 milliamps. Now this is not one of our current that they want us to find, but it might be useful, right? So we know IA equals negative 5 milliamps. Now when we look back at our KCL equation for node 2, right, which is this node, we have a relationship between IA and IY. So because we found IA, we can now plug in the value of IA and find IY. Therefore, I'm just going to plug in negative 5 milliamps into this equation. So now I'm going to write this as 5 times 10 to the minus 3 plus IY, which we know equals IA, and that's going to be negative 5 times 10 to the minus 3, right? Now we're going to find for IY. So when we manipulate this equation now, we're going to have IY equals, we have negative 5 times 10 to the minus 3 minus 5 times 10 to the minus 3. Therefore, IY is going to equal to negative 10 times 10 to the minus 3 amps, which we know is going to be written as IY equals negative 10 milliamps. So this is the second current they wanted us to find. And remember, because this current is negative, IY is not going in this direction. IY is actually going to go in this direction. And when you think about it, that makes sense, right? Because when we took the KCL equation for node 1, all of the currents seem to be leaving this node, which made no sense. Because if all of the currents were leaving this node, how did current get to this node? So in reality, when we worked out the current for IY, this made perfect sense. So the current actually isn't going this way. The current for IY is going this way. All right, now let's find the last current, which is IZ. Now when we go back to our KCL equation for node 1, which is right here, we have a relationship between IY and IZ. So because we found the current in IY, which we know is negative 10 milliamps, we're just going to plug that into this equation here. But before we substitute in the value of IY, I made a mistake. And I just saw it. So now I'm just going to do this all over again, right? Because I have negative 12 times 10 to the minus 3 when this was actually supposed to be positive the entire time. So let me just erase all of this, and I'm just going to do it all over again, right? So KCL at node 1 was basically the same thing. We know the current entering node 1 was 0 equals the current leaving. I had negative 12, but instead of it being negative 12, it was supposed to be 12 times 10 to the minus 3 plus IY plus IZ. So this is the correct equation. Once again, I only had a negative sign. It's supposed to be positive. Now what I'm going to do now is I'm going to substitute in the value of IY. We know the value of IY is negative 10 milliamps. So what I'm going to do now is I'm going to substitute in the value of IY. Now when I substitute in IY, I'm going to rearrange this equation to make IZ the subject. So I'm going to have IZ equals negative 12 times 10 to the minus 3 minus, we know IY is negative 10 milliamps, so we're going to write this as minus negative 10 times 10 to the minus 3. Now when you solve for this, IZ is going to equal to negative 2 milliamps. So this is the current flowing through IZ. Now that we have solved for IZ, we have successfully completed this problem. We found the current IX, which is 9 milliamps. We found the current IY, which was negative 10 milliamps. And we found the current IZ, which was negative 2 milliamps. So this is how you solve this type of problem. Once you have a situation where you have an essential node, you can always use Kirchhoff's current law to find a current in a branch that is attached to that node. So just remember Kirchhoff's current law. The total current entering a node is going to equal the total current leaving a node.